Hey there. If you've ever stared at the periodic table and felt like you're just supposed to memorize a giant list of rules and exceptions, well, you've come to the right place. We're going to treat this whole thing like a puzzle. And the best part, once you understand just two key ideas, the entire board just clicks into place. Okay, let's get into it. So, does this sound familiar? You're looking at the table, trying to remember if atomic size goes up or down across a period, and you're wondering why on earth electronegativity and electron affinity sound almost identical but are totally different things. Trust me, you are not alone in this. It's a classic chemistry headache. Yep, these are the usual suspects, right? Juggling the trends, remembering the very specific definitions, trying to keep ions straight, and then you get hit with the exceptions. It can feel like a lot, but what if I told you there's a much simpler way to look at all of this? So here's our game plan. We'll start with the two big rules that basically solve the whole periodic puzzle. Then we'll use those rules to figure out how to size up atoms and understand the electron tug-of-war. We'll wrap up with a quick cheat sheet and, maybe most importantly, talk about why any of this actually matters. All right, let's do this. This section is the absolute key. This is the why behind every single trend. I want you to forget about memorizing a dozen different things. If you can just get a handle on these two opposing forces, you'll be able to figure out the entire table on your own. I want you to think of every atom as a constant battle between a pull and a push. It's that simple. On one side, you've got the inward pull. As you get more protons in the nucleus, that positive charge gets stronger and it yanks the electrons in tighter. The fancy name for this pull that an electron actually feels is the effective nuclear charge, or ZF. On the other side, you've got the outward push. All the electrons in the inner shells basically create a shield, blocking the outermost electrons from feeling that full, powerful pull from the nucleus. So here's the bottom line. Every single trend we're about to talk about is just the result of which of these two forces is winning that battle. And this right here really nails the power of that outward push. See, it's not the electrons hanging out in the same shell that do most of the work. It's those completed, full inner shells that are the real experts at shielding. Grasping this idea is the secret to understanding why trends going down a group are so often the exact opposite of trends going across a period. Okay, let's put our two rules to the test. First up, atomic size. How big is an atom really? And what happens to that size when it turns into an ion? Since atoms are basically these fuzzy clouds of electrons, you can't just take a tiny ruler and measure one. So chemists came up with a pretty clever workaround. They take two of the exact same atoms that are bonded together, measure the distance between their centers, and then just chop that number in half. That gives us what we call the atomic radius. Now let's use our rules. What happens as we move across a period, from left to right? Well, we keep adding protons, right? That means the inward pull from the nucleus gets stronger and stronger. But, and this is key, we're adding electrons to the same outer shell, so the shielding doesn't really change much. The pull wins, and the atoms actually get smaller. Now, what about going down a group? Every time we step down, we're adding a whole new shell of electrons. That new shell gives a massive boost to the outward push from shielding. In this case, the push wins, and the atoms get bigger. See? No memorization, just logic. So what happens with ions? Let's look at sodium. As a neutral atom, you've got 11 protons pulling on 11 electrons. It's balanced. But when it loses an electron to become a positive ion, a cation, suddenly those same 11 protons are only pulling on 10 electrons. That inward pull just got way more effective for each of the electrons left behind, so the whole ion just shrinks. And, you guessed it, the exact opposite happens with anions, or negative ions. Fluorine grabs an extra electron to become F-. Now you've got 10 electrons being pulled by only 9 protons. But even more important is that you've just shoved an extra electron into an already crowded space. This cranks up the electron-electron repulsion. They all start pushing each other away, and the whole electron cloud just puffs up. Anions are always bigger. All right, let's move on. We're going to apply these same rules to probably the two most mixed up concepts in all of general chemistry, electronegativity and electron affinity. Just think of this as the ultimate tug-of-war for electrons. Okay, this table is fantastic because it just cuts right through the confusion. Here's the deal. Electronegativity is all about how greedy an atom is for electrons when it's already in a bond, sharing them with another atom. It's a relative ranking, not a measurement, so it has no units. Electron affinity, on the other hand, is the actual measurable energy change that happens when a single, isolated atom floating around as a gas gains one electron. It's a real energy value. So one is about sharing, the other is about gaining. Big difference. And this brings us to that famous exception that trips everybody up. So fluorine is the undisputed champion of electronegativity. It is the absolute best at pulling on shared electrons in a bond, no contest. But when you look at the raw energy released from gaining just one electron, chlorine actually has it beat. So why is that? Well, fluorine is just so incredibly tiny. Its electrons are crammed into a really small space. So when you try to add a new electron, there's a little bit of repulsion. It's like trying to get on an already packed elevator. Chlorine is a bit bigger, so it has more room to welcome that new electron in. So, we've gone deep into the why behind all these trends. Now let's pull back and put everything together into a super practical summary that you can actually use to study. And there you have it, all in one neat little table. As you go across, that stronger nuclear pull makes atoms smaller and way more electronegative. As you go down, that extra shielding makes them bigger and more metallic, meaning they're more likely to give up an electron. It all comes back to that same simple push and pull. And before we finish, here are 3 common traps to watch out for. First, be really precise with your definitions. Details like isolated gaseous atom actually matter a lot. Second, don't mix up your rows and columns. Groups go down, periods go across. And finally, the most important one, please don't just memorize. If you get stuck on a test, don't guess. Just go back to the why. That inward pull versus the outward push will always show you the way. So, we've taken the puzzle apart and put it back together. But you might be wondering, why is this so important once you leave the classroom? The thing is, these trends aren't just abstract rules for an exam. They are, in a very real sense, the fundamental operating system of the universe. An element's size and how badly it wants electrons dictates literally everything about how it behaves. It's why salt dissolves in water, why some reactions are explosive, and why others don't happen at all. So, the next time you look at the world around you, from a simple glass of water to the complex molecules that make you you, I want you to remember that it's all built on this incredibly elegant, predictable tug-of-war happening on a scale that's almost too small to imagine. That simple push and pull between a nucleus and its electrons, well, it turns out that's what builds everything.